Resume. All right. It's time to talk about something a little more uplifting. Yeah, I know. So buoyancy is a force that exists. It's a contact force caused by being in a fluid. So you'd have fluid touching the object on all or on many sides. And Archimedes' principle guides us on how to think about buoyancy. Archimedes was an ancient Greek, and they built boats and stuff. So they had an idea of how buoyancy in water worked. And the principle is that the force of buoyancy is equal to the weight of displaced fluid. Now that leaves a couple of questions. And one of those questions is, how do we relate the displaced fluid to its weight? How do we model the weight of displaced fluid? So that's the first thing we need to answer. And the answer is that we need to find the mass of the displaced fluid and then multiply it by G. But then how do you know the mass of the fluid? Well, there's a nice quantity that relates to fluids called density. And we like the quantity density because it's an intrinsic quantity. And having an intrinsic quantity basically means it doesn't depend on the sample size. So if I measure the temperature in this room, I'd get a value of around probably 75. And if I just drew a curtain across half the room and measured each half, I would still measure 75 in each half. There's nothing about the temperature would cut in half just because I divided the room into two parts. That is an intrinsic quantity. And water is a fluid, and you can take a bucket of water, measure the density, and then take half of the bucket of water or a cup of water and measure the density. Or you could take a swimming pool full of water and measure the density, and you'd basically get the same result. Density is an intrinsic quantity. So density is symbolized by the Greek lowercase letter rho, which looks like a curly letter P, kind of like that, is equal to mass per unit volume. And that could be, like I said, a little bit of something or a lot of it. You just have to make sure that the mass and the volume go with each other. You can't use the mass of a cup of water and the volume of a swimming pool of water together in a density formula and expect it to be meaningful. So that means that for any object, the mass is equal to the density times the volume. And that's what we're going to use for the force of buoyancy. We're going to plug that in up here and put in the density of the fluid times the volume displaced times G. Oops. So just kind of describing what my symbols mean in this particular situation. So then now we have a way of describing the force of buoyancy in a little bit more detail. That also leaves a question. How do we know how much fluid is displaced? So I'm going to rewrite this formula because it's going to scroll off the screen. Density of the fluid, volume displaced, G. There's basically two situations that you could be in. You could have a situation where you kind of control the amount of volume. So that could be the given quantity. And if you have an object that's completely sunken, then the volume you're talking about is the volume of the object itself. So you could be controlling the volume based on the fact that you know how big your object is. So you could take a cannonball and sink it in water. And before you sink it in water, measure the size of the cannonball so you know how big it is. And when you sink it in water, thus you know the buoyant force, because you can put in that volume that you calculate and the density of the water and G, and you got your buoyant force. Or you could do a backwards calculation. You could know the amount of force that's involved. For a floating object, like a block of wood that is thrown into water, it kind of determines exactly how deep to float in the water. And only the portion of the block that's actually under the surface counts as displaced volume. The part that's sticking up doesn't count. And for a floating object, the buoyant force is equal to the weight of the object. And we'll see these things in a little bit more detail when I do some diagrams and force diagrams. Now, usually in thinking about buoyancy, I compare the buoyant force to the mg force. So I want to think about also the force of gravity, which is mg. Now, this isn't fluid. This is our object. So maybe I could use an O subscript on the object. And just like for the fluid, I could split up the mass of the object into a density times a volume. This would be the density of the object times the volume of the object, still times G. Now, the reason I want to do this is because now I have two analogous formulas, one for one force, one for the other force. And having formulas that have the same structure makes it really easy to compare them to each other. Now, in order to know how they're supposed to relate to each other, I need to think about how these forces affect the object and any other forces that may exist. And that requires force diagrams. Question? If the buoyant force is greater than the force of gravity, then between the two of them, there would be an upward force. Yeah. Now we're going to do all static situations. We may do like two different situations where you have a boat that's unloaded and a boat that's loaded, but we still want to do our analyses for static situations. In static situations, the net force is 0. But there may be more than one force. So I'm going to think about the possible force diagrams for a static situation. And one possible force diagram is for a floating object. Another possible force diagram is for a submerged object. And the third force diagram is for a boat with cargo. So I want to go back and forth between these situations. Let's first do all the force diagrams. So the easiest force diagram is for the floating object. For a floating object, we have our object and we have our force of gravity and we have our force of buoyancy. And that's it. Just two forces. And that's the easy case where we know these two forces are equal because we observe the object to be stationary. Therefore, we know that the acceleration is zero. Therefore, we know the forces are balanced. So that's the easy case. For a heavy object, you throw it into the bucket or into the lake, it sinks to the bottom. Or maybe it's hanging from a string and you dunk it and it is still hanging from the string, but now it's underwater. The object is now submerged. So in this case, we have a really strong force of gravity and not enough force of buoyancy by itself. So there needs to be an extra force. At first, the object can go downwards, but then it gets to the bottom and there's a normal force. So let's put in a normal force, F sub n.
So submerged means when it is underwater.
It's underwater, it's come to rest, and it is a fixed amount of being submerged. Like you could have an object that's half submerged or completely submerged. Often we talk about objects that are completely submerged underwater. Right. So we could say, or F sub t. Depends on what situation you're in. Now I want to jump over and think about the boat with cargo. Now, the boat with cargo feels a downforce from the force of gravity. That's m boat times g. And I'm putting the mg there to try to make it clear exactly what force I'm talking about. But this boat has cargo. So what's the cargo do to the boat? It pushes down. I know this because the cargo is sitting off the side feeling an up force from the boat. So a traditional name for this is load, F sub L. You load the boat with cargo and it's carrying the load. So now we know that boats can carry cargo. We've seen it. The reason the boat doesn't sink is because of the buoyant force. So the boat has this giant buoyant force, F sub B, that is pointing up. So you can see in all these diagrams, there's an upward buoyant force and a downward gravity force. And the difference is, are they the only forces, or is there an extra up force because you have a heavy object that sunk and reached the bottom? Or is there an extra down force because you're floating, but somebody's trying to push you down? The cargo is trying to push the boat down. And then that forms our Newton's second law equations for the three situations. This is F sub B minus F sub G equals 0. In other words, F sub B equals F sub G. In the submerged case, formally, it's F sub B plus F sub N minus F sub G equals 0. In other words, F sub B plus F sub N equals F sub G. And then in the boat with cargo, we have F sub B minus F sub G minus F sub L equals 0. Or the buoyant force has to make up for both gravity and the weight of the load. In a sense, the regular floating object equation and the boat with cargo equation look very similar to each other. They're both saying the buoyant force has to carry the weight. The buoyant force has to carry just the weight of the boat, or the buoyant force has to carry the combined weight of the boat and the cargo. So now there's a question of how do I analyze these things? In each situation, I like to compare the buoyant force to the gravity force, but we have different ways of comparing numbers. Sometimes we compare numbers just by holding them up to each other and putting an equal sign in between. We make an equation out of it. And that's what I do with the center situation. I'm going to compare the two forces by plugging in their formulas and setting them equal to each other. So we compare these in the equation. So this is rho fluid V displaced G equals rho object V object G. So I'm plugging in a formula for each of those two forces, and now I get a relationship between densities and volumes. So we'll do an example in a minute once I finish filling out this table that shows how we make use of this. But it turns out to be pretty easy to use. This is basically a set of ratios that's already been cross-multiplied. So we're going to turn it back into ratios again, and makes it really easy to use. It's not really fluid dynamics, it's fluid statics. Fluid dynamics involves velocity and resistance forces that depend on the velocity. If you stick your hand out the window and you're driving slow, you feel a little breeze. If you stick your hand out the window and you're driving really fast, you can feel the wind pushing on your hand. Don't stick your hand out the window of a moving car. It's not safe. One time, my wife stuck her hand out the sunroof and a bee hit her in the palm. Moonroof. Yeah. And the bee's leg ended up embedded in her palm, and it caused an allergic reaction similar to a bee sting. And you never know what may hit you if you stick your hand out the window of a moving car. This is another one of those things where I have to put disclaimers out when I say things. Yeah, that could happen too. No. All right. Sometimes we compare numbers by dividing them. And when you take a ratio of things, that can often produce useful results. So I basically use the force balance equation to relate known information to unknown information. But then I'm going to compare my force of gravity divided by my force of buoyancy. Now that's just one side of a fraction of an equation. And usually I'll know one side or the other of the equation, and I can use this equation to find the unknown thing. So on the other side of the equation, I'm going to plug in my object's force of gravity. That's rho object V object G. That's the actual weight of the object, like when you measure it normally in air. And then on the bottom of the fraction, I have rho fluid V displaced G. And the G's cancel. And the V's often cancel. Because when you sink an object, it has a certain size. When you submerge it, it pushes an amount of water aside equal to the size of the object. So if your object is 100% submerged, then those two volumes are equal. Then you get a ratio equation that relates forces with densities. And you find that the ratio of the force of gravity, that is the weight of the object divided by the buoyant force, is equal to the ratio of the object's density divided by the fluid's density. And then the third situation, I compare using the third method we have. I compare by subtracting. Sometimes we subtract things to answer the question, what's the difference? So we do a lot of that. And in this case, I'm going to think about two situations. One situation with some cargo and one situation with more cargo, or one situation with cargo and one situation without cargo. So I'm going to think about delta force buoyancy in two situations. And in these two situations, it's going to be the same boat. So the force of gravity on the boat isn't going to change because it's the same boat with the same mass. So the force of gravity doesn't change from one situation to another. The delta is 0. But the load does. Delta force load. So we're going to have a different load. Maybe the load is 0 in one situation and a bunch of cars in a second situation. Now over here, this is going to be delta force buoyancy is equal to density of fluid times delta V displaced times G. And the only difference in the buoyant force in these two situations is that the amount of displaced volume changes. When you load cargo on a boat, the boat subsides in the water a little bit. When you step into a kayak or a rowboat, the kayak or the rowboat sinks a little. I don't like to use the word sinking with relation to boats because it has a specific connotation. So I say it subsides a little. And then we could relate the delta V displaced, since V displaced is some area times depth, delta V displaced is some area times delta depth. So the changed load causes a change in the displaced volume, which causes a change in how deep the bottom of the boat is. And maybe the bottom of the boat hits, or maybe it's still floating overall. All right, so now we need to do a couple of numerical examples. And by far, the most important numerical examples are the ones dealing with the first two situations. So let's take a look at some typical examples. So let's say that a block of ice floats so that about 9% of its volume sticks up above the surface. I think it's like 10% sticks up above the surface. That's the thing they call the tip of the iceberg. So the density of pure water is 1,000 kilograms per cubic meter. This desk I stand in front of every day is about 2 meters wide, 2 meters deep from front to back, and 1 meter deep and 1 meter tall. This is about 2 cubic meters. If this was a fish tank, the size of this desk, it would be 2,000 kilograms, which is 2 tons, 2 metric tons. Metric tons are close to imperial tons. So anyway, we now have all the information we need to think about the density of that ice. So the first thing we need to realize is that if 9% of it is sticking up above the surface, that means 91% is underwater. That's the displaced volume. And I can even form that into equations. I could say that V displaced is equal to 0.91 of V object. Our object is the ice. Or I could say that V displaced over V object is equal to 0.91. And then the second thing I want to realize is that since this is a floating object, Newton's second law is pretty straightforward. It means that the force of buoyancy minus force of gravity equals 0. That's what I wrote up above. Still true for a floating object, which means that the force of buoyancy is equal to the force of gravity. And I can plug in the force of buoyancy here. Rho fluid V displaced G equals rho object V object G. Now there's a couple of ways I can go with this. I can do direct substitution right now. And I can say that rho fluid times 0.91 V object times G is equal to rho object V object G. Now I can do a bunch of canceling. I can cancel the G's and I can cancel the V objects. And I find that 0.91 rho fluid is equal to rho object. Plug in the 1,000 and I get 910 kilograms per meter cubed is the density of the object. So that's one fairly straightforward way to think about this situation. And it basically comes down to you take your density of the fluid and multiply it by the submerged fraction, and you get your density of the object. The other thing we could do is we could just solve algebraically for density of the object. And that would be rho fluid V displaced G over rho object V object is equal to, wait, I was solving for rho object. V object G, I'm dividing by that. That's rho object. There. So I divided by the two things that used to be multiplied by the object density, and then the G's cancel, and I get rho fluid times V displaced per V object, and that is my density of the object. And that also is the same equation. So when you do algebra work, there's always choices involved in how you do your step-by-step process. But if you're doing consistent algebra, you should always end up with the same thing. And one of the keys to dealing with the floating object, again, is to recognize the difference between the portion of your object that is sticking up above the surface and the portion that is under the surface. They have to total 100%. Usually you're thinking about the part you can see, and usually you're above the water. So you see the portion that sticks up, the 9%, and you have to convert that to the 91% because that's the part that fits into the formulas, is the displaced portion. Yeah? So the fluid density is 1,000.
Oh, that's right.
Yeah. So I just plugged in my 1,000 here and got that with units. Yeah. Now, if your fluid is different, then you plug in a different fluid there. The other, so this is an example for a light floaty object like ice or wood or something like that. The other case is a heavy sinking object. So let's do an example for that. So we're going to take a 20 Newton object that's kind of dense. So a 20 Newton object is about like 4 or 5 pounds. So it's not super heavy. And when you submerge it, it gets just a little bit lighter. So this is actually describing two different situations. One is mg, and say a force of tension is 20 newtons. So this 20 newtons is talking about a regular, everyday, hang your object from a scale experiment or place your object on a scale experiment. And what this tells us is that the mass times gravity is equal to 20 newtons. And that value for the object doesn't change unless your object is like permeable and becomes waterlogged. Then there's questions as to what constitutes the object and whether the water that comes in and becomes part of the object or not. The second part, the 19 newtons, is talking about a different experiment. We take this heavy mg equals 20 object and submerge it. Now there is a force of buoyancy, but there is also an upward force tension is equal to 19 newtons. So we have this 19 Newton force that's over here. And that allows us to determine that the force of buoyancy is equal to how much? 1 Newton. I could build Newton's second law and plug in and show how I solve, but I think it's fairly clear what's going on here, that the 19 newtons needs some extra up force to cause balance, and the difference is 1 Newton, so that has to be 1 Newton. I choose easy numbers to try to make it easy. So then the third phase of this is to compare the force of gravity to the force of buoyancy. And that is rho object v object g over rho fluid v displaced g. So that's using raw equations from the equation sheet. And I'm just declaring my intent to do this. And when I do this, this is how it's going to work out. Now I can start filling things in. 20 over 19 is equal to density object over 1,000. All of a sudden, I have an equation that I can solve for the density of my object. Oh, wait. B isn't 19, it's 1. Sorry. That's what happens when you just look and grab numbers without thinking about the numbers that you're grabbing. So this is supposed to be the force of buoyancy in the denominator, which we learned was just 1. Yes. So now we just multiply both sides by 1,000 and we get 20,000 kilograms per meter cubed is the density of our object. There's this apocryphal story about a scientist who was asked to verify that a crown of gold was actually gold, and maybe it was Archimedes, but he decided to do this experiment on the crown of gold and determined the density of this crown of gold and found out that it wasn't gold, it was lead. And then the metalsmith was executed for giving the king a fake crown or something like that. So no, it's not really that poisonous if you eat it. It's poisonous if the lead is oxidized and then you ingest or breathe it. Metallic lead isn't dangerous. Oxidized lead is dangerous. Of course, the chemists will know whether lead in your digestive system will become oxidized or not. I don't know. I don't know. It's lead oxide that we used in paint, because lead oxide is this white powdery stuff that makes a wonderful base for paint. And all you have to do is add a little dye and you can make your walls nice and pretty. But apparently children shouldn't eat it. Yeah, it's not just lead paint, it's also lead in gasoline. So I watched a video recently describing who killed the most people in history, and it was the guy who invented the lead additive to gasoline. Yeah. So like when I was a kid, one car had to get the leaded gas and one car had to get the unleaded gas. Yeah. I don't know. I have quirks. I have quirks. All right. So we have two different, very common buoyancy situations, and they're both going to be on the test. So basically everything I've done today in these two examples, that's going to form two test questions. Yep. All right. Let us call it a day.